Remember the Pythagorean Theorem from high school?
Anyone? Anyone?
This was the result that the squares of the two shorter sides of a right triangle equal the square of the longest side. It's named for the Greek philosopher and mathematician Pythagoras, who lived around 500 BC, even though the theorem itself seems to have been understood as much as 1,000 years earlier. Now, why should we care about the Pythagorean theorem? Why is it interesting?
Well, for one thing, even though this is a very familiar fact, you probably do recall from your geometry class or your trigonometry class, it's actually a kind of non-obvious fact.
If you think about it, why should it be that the areas of these two squares add up to the area of this bigger square instead of adding up to something else? It's kind of surprising, actually.
So this gives us an opportunity to think about how we know this is true. That is, what it means to prove something mathematically and what a mathematical proof is. Second, the Pythagorean theorem is used in some very interesting applications. Perhaps one of the most interesting is that it is central to working out how much time slows down when objects are moving, a part of Einstein's theory of relativity. You can learn more about that in another video.
There are many, many different proofs of the Pythagorean theorem. The most famous proof comes from Euclid's Elements, a Greek geometry textbook written around 300 BC. Here's the diagram for that proof from one of the oldest manuscripts we have of Euclid's Elements, a manuscript that was written in Arabic. But this proof is actually a bit complicated. We're going to look at a much simpler, easier to understand proof that is sometimes attributed to Pythagoras himself. Here's the proof. First, draw a square. Then, pick some point along one side of the square and mark it. Then mark the same point, the same distance along each of the other three sides. And draw straight lines connecting adjacent marks. Notice that we now have a smaller square inside our big square, and that the sides of the smaller square are the same length as the longest sides of the triangles. So this square is the big square in the Pythagorean theorem. Often we'll put tiny squares to mark the right angles, the perpendicular angles of the triangles, and of course we know that they are right angles because we started with a square. Next we move the triangles. Now what we have is two smaller squares inside the big square, each of which has a side equal to one of the two shorter sides of the triangle. So these are precisely the two smaller squares in the Pythagorean theorem. Since all we've done is move triangles, the part of the big square that isn't contained in the triangles has to be the same in the two arrangements, and that proves the Pythagorean theorem. The area of the one interior square in the first arrangement has to be equal to the areas of the two interior squares in the second arrangement. Often you'll see the sides of the right triangle labeled A, B, and C, with C for the long side. And so your high school math teacher almost certainly wrote the theorem on the board as A squared plus B squared equals C squared.
So, as I suggested earlier, with this example, we can think about the nature of mathematical proof. What we have is a series of steps, each of which seems indisputably, clearly, intuitively correct.
And since the steps each logically follow one from the other, we feel compelled to accept the entire argument as true. And so accept as true a non-obvious, although familiar result, like the Pythagorean theorem. Well, at least non-obvious to me. Maybe someone more intelligent, or a hyper-intelligent alien, or an alien with a different type of mind might find the Pythagorean theorem super obvious and therefore could dispense with the proof.
So is this proof reliable? It seems to be, and yeah, pretty much it is. But it's worth understanding that it relies on assumptions. unstated assumptions, maybe even any number of unstated assumptions.
One so far unstated assumption is that the triangle is on an unstretched, undistorted surface. Clearly, if we could stretch and distort the surface that the triangle is on, then we can give the sides of a triangle with the same angles all sorts of different lengths, and so the Pythagorean theorem wouldn't even necessarily be true.
This might seem like an academic point, but actually the space that we live in is distorted in exactly this way. Anytime that there's gravity, then space is distorted like this. That's a part of general relativity. So for us, the Pythagorean theorem is actually only approximately true, although very nearly, almost exactly true.